high frequency transistor so let's start with the BJT. Okay. So our high frequency model is going to look like this. And these are small signal models. So we have our base terminal, and then we have our resistor R pi, over which a voltage drop of VBE occurs. And then in parallel with that resistor, we are going to have a capacitor now, which we are going to call C pi. And we're going to talk about where these capacitances come from based on our model in a moment, okay? Over here, on the right-hand side, we have GM VBE. And so down here in the middle is our emitter terminal. In parallel with GM VBE, we have our early effect resistance R naught. And then here's our collector terminal. And we are also going to have a capacitance CS here from the collector to ground. And then lastly, we are going to have an internal capacitance which acts as feedback between the base and collector terminals called C mu. So this is what our high frequency transistor model will look like. Okay. So let's talk about these individual capacitances. The first one that we're going to talk about is the capacitance C pi. Okay. C pi is between the base and emitter terminals, and it represents the combination of the charge storage mechanisms that occur within the base emitter junction and the junction capacitance. So I'm going to draw our big ugly BJT model again. And let's say that here is a transition. Here's a transition like so. And we're going to put our emitter terminal down here, our collector terminal over here, and our base terminal down here. And these dashed lines here represent the width of the depletion region for the base emitter junction. And these guys over here represent the width of the depletion region for the base collector junction. Our emitter is N-type, our base is P plus, and our collector is N plus plus. Okay. So let's talk about when this guy is in the forward active mode, right? So the forward active mode, just to refresh you guys, because it's been literally months since we talked about these things, means that this junction, the base emitter junction, is forward biased. And this junction, the base collector junction, is reverse biased, right? So we'll have a voltage VBE that's greater than 0. And we'll have a voltage VCB that's also greater than 0, like so. And did I get the emitter should be the one that's most heavily doped, right? Not the collector. I think I got those backwards. Because the emitter is where all the charge carriers are coming from. So the emitter should be the most heavily doped, the collector should be the lightest doped. I apologize for that. So if we look at concentrations here, the blue line is representing electron concentration, and the red lines are representing hole concentrations in each of these regions, okay? So when our base emitter junction is forward biased, we know that electrons can easily diffuse from the emitter into the base, and similarly, holes can easily diffuse from the base to the emitter. So we're going to have a charge here that I'm going to call QDP, okay, which represents excess holes above the, I guess you call it extrinsic carrier concentration of holes in this region, right? So these are the minority carriers that have been injected into the emitter region. And similarly, we're going to have minority carrier injection occur over here. I'm going to call this QDN. And we talked about the concept of minority carrier injection in 335. In addition, we have a layer of storage charge. I'm going to call QBEP here, and a layer of stored charge here, which I'm going to call QBEN. So we have injected minority carriers on both sides of the junctions, so that's a charge storage mechanism. And then we also have a layer of stored charge representing our junction capacitance. Okay. These are voltage controlled relationships. So anytime that we have an amount of charge that depends on the amount of voltage applied, we model that as a capacitor. So excuse me. For an NPN transistor, the stored electron charge in the base, QDN, is equal to tau F times IC, where tau F is the forward base transit time and represents the average time the charge carrier spends crossing the base, typically on the order of 1 to 100 picoseconds. Okay. Since our collector current IC is exponentially related to our voltage VBE, QDN must also depend on VBE. So from this, we can define a small signal diffusion capacitance, CDE, as the derivative of QDN with respect to our base emitter voltage which is then simply tau F times the derivative of IC with respect to VBE, or tau F times the transconductance of our BJT, or finally tau F, which that does no longer looks like a tau, times IC over our thermal voltage. So we are modeling the capacitance of this stored minority charge. Okay. As CDE. Now we're going to revisit our junction capacitance. So the base emitter junction capacitance, CJ naught, occurs due to the stored charge in the depletion region of the base emitter junction. Since the base emitter junction is forward biased, CJE will be larger than CJ naught, right? So CJE, which is going to be the forward biased junction capacitance, is CJE naught, which is the unbiased junction capacitance of the base emitter junction, times 1 plus VEB over V naught E, where V naught E is the built-in voltage of the base emitter junction. So this is all stuff that we've dealt with before, except that I'm now using a subscript E to clarify which of the two junctions I'm talking about here. To the nth power, which I believe, I don't remember if we talked about linearly graded versus step graded junctions in 335 or not. We might have just thrown all of that under square root of sine and moved along. Do you guys remember? Okay, so effectively all M here depends on is what type of junction that we have. For a step junction, M is 1/2, and for a linearly graded junction, M is 1/3. Okay, which is how this winds up being the exact same equation we had before. So a step junction means we treat it as if a piece of P-type material is abutted directly next to a piece of N-type material. And a linearly graded junction just means that the concentration of dopants gradually changes from one side to the other. In truth, the overwhelming majority of PN junctions are linearly graded junctions, but the math is slightly easier for step junctions, which is why we usually use those in classes. Yes.
What is in your sentence up there where IF?
Tau.
Oh, okay.
Tau F,
All right.
which is this guy right here, and then here, and here, and here.
Yeah, that's what I was thinking. I just wasn't sure. I was like, backwards J. That's on me.
No, tau. Greek letter tau.
Gosh, thank you.
Yep. Okay. So, Luke. So it's representing, honestly, I couldn't tell you what D and E, well, I guess D stands for diffusion. And the E is because it's occurring at the base emitter junction. All of these junctions are going to be base something, so we're just throwing away the B part. So this E here is meaning it's a base emitter junction. This D is because we're talking about, and I'm positing here, I can't be 100% sure because I didn't come up with this nomenclature. But we're talking about the charge that is injected into both sides because of diffusion that's going on. So I would believe that this is a diffusion capacitance. And I know for sure that this is a junction or depletion capacitance. All right, so we are going to approximate CJE naught as, excuse me, CJE as twice CJE naught. Okay, so let me explain where this assumption is coming from. The quantity VEB right here, which is controlling this capacitance, is a negative quantity because our junction is forward biased. So we're making this portion here take away from 1, making the overall junction capacitance larger. And for simplicity's sake, we're going to say that it's going to be roughly this, because there comes a certain point where we can't make that junction, the width of the junction, any smaller without messing things up. Okay. So we're going to assume we're operating at a point in forward bias where the depletion junction capacitance is roughly twice as large as it would be if we didn't have a bias voltage applied to it. Okay. Since both of these capacitances are related to the base emitter junction, they appear in parallel. From this, C pi is simply the sum of CDE and CJE. So we lump those two guys together. So if we look back at our original model, we now, I hope, have at least a rudimentary understanding of where this guy is coming from. So this capacitance exists because we have charge storage in our base emitter junction under forward bias conditions. All right, now we're going to talk about C mu. So C mu is the capacitance seen between the base and collector terminals. And it occurs due to the charge stored in the depletion region of the collector base junction. Okay. So this is a reverse bias junction where we have some amount of charge stored on each side of that junction, right? So we could call those, let's see, Q, BCN, and Q, BCP. And C mu is just a junction capacitance. So it's going to look like CJC naught, where CJC naught represents the junction capacitance of the base collector junction at zero bias, divided by 1 plus VC over V naught to the S power, where that V naught S again represents the built-in voltage of the collector base junction. Okay. So C mu occurs because we have this charge stored, which depends on this voltage VCB. So we've got 2 out of the 3 taken care of. The last one that we have to deal with is related to the junction capacitance that we see with the substrate of our device, okay? So over here on the right-hand side, so I can wrap this up on a single page thing. If we were to draw a BJT, where here is our P substrate, we would have, make sure I'm using the right colors here, and I'm not. We would have our emitter region, which is doped very heavily N-type. We would have our base region, which is doped P-type. And then finally, that's drawn crappily, but it'll get the job done. We have our collector region, which is C-type, right? So the junction between the emitter and the base contributes to C pi. The junction between the collector and the base is what C mu is. Well, there's a junction between the collector and the substrate as well, because this is N-type and this is P-type. And so there's going to be a depletion capacitance here also. That's what CCS represents, okay? So it's a whole lot of depletion capacitance. So CCS, sorry, this should be C here. I don't know why I thought it was S. Will be CJS naught divided by 1 plus VC over V naught S to the nth power. So effectively, we have 3 different junction capacitances, and I apologize for messing up some of my subscripts here because all of these equations are so damn similar. CJS naught represents the junction capacitance observed between the collector and the substrate, where VC is the collector voltage with respect to the substrate, which is always going to be at ground, which is why we don't have a second subscript here. So this is C measured with respect to 0, our substrate potential, divided by the built-in voltage of this junction. Okay. So that is where all of our BJT capacitances come from. How did I wind up on page 12? All right, let's go back to the beginning. Oh, I must have hit the button where I just skipped to the last page instead of skipping to the next page. Okay, so for me, it's going to be crazily out of order. For you guys, you can, do whatever you need. Yes, sir.
What frequency is high frequency?
That's a fantastic question. Okay, so the answer, and you're going to hate this so much, is it depends. All right. So as a we still have more to talk about on this, but as a preview of what we're going to begin talking about on Friday, and I hope to do this by literally simulating the circuit that I asked you guys to design and specify for design project 1. What you should observe, this is a tangent, you don't have to write any of this crap down, I'm just trying to answer your question, is that if we looked at the gain AV of a transistor circuit as a function of frequency, where this is frequency, what we should observe, and let's just say that it's a simple single transistor circuit, is something like this. Imagine that line is flat. And this is a shitty looking Bode plot because I can't draw, but that's what it's meant to be, okay? So let's define these regions. This is going to be our low frequency region. In this region, all of those capacitors that we used in our DC biasing thing to separate our DC signals from our AC signals, this is where they're relevant, okay? This region right here, where the gain is effectively constant, mid-band, not mid-bang, that's weird, sorry. This is our mid-band region, okay? The mid-band region is where we've derived all of those voltage gain equations to be. So we are beyond where our low frequency capacitors are able to do anything. So we can treat them all as open circuits. But we're at a point where all of our high frequency stuff looks like short circuits. Actually, no, I got that backwards. All of these look like short circuits. All of these still look like open circuits. And then finally over here, we have our high frequency region, where all of the internal capacitances of our transistors start to affect the device's behavior. Okay.
So that's why we start losing gain to stuff like R pi is shorted and R naught is shorted.
Right.
So
They start going from looking like an open circuit in parallel with it to having some finite impedance to eventually looking like a short is directly in parallel with it. You're 100% right. So we are talking specifically about this area because it's the only one that we don't really know anything about. Because these capacitors we choose, we have control over them because we physically place them in the circuit. In this region, all of these capacitors look like shorts and all of the capacitors over here look like open circuits, so they really don't contribute anything. Our mid-band gain is literally what we spent all of 335 talking about. And now we're moving over here to better define what these guys look like when the internal capacitances of our transistors start influencing the behavior of our circuits. And we are going to, when we get to the frequency response stuff, we're going to analyze circuits at low frequency and then also high frequency because they're going to behave differently because of the way that the capacitors are connected, right? Because we choose how these are connected. We have no choice as to how these are connected. So that's a very good question. One lecture too early, but that's okay. All right.
Those are like really small capacitors.
Yes. Like typically on the order of pico and femtofarad capacitors. So very, very small.
So would the only way to change your high frequency stuff would be physically change the circuit?
So that's also a super good question that the third part of this class is all about. So when we're going to talk about things like feedback amplifiers and stuff like that, like effectively what's going to happen is that every capacitor in these circuits is going to cause either a pole or a zero in our frequency response. Sometimes these poles and zeros are in convenient places, and other times they are not, and they cause the circuit to behave very poorly. So we are going to learn about a concept called Miller compensation, or excuse me, the Miller effect and frequency compensation, where effectively, I have a lecture sitting here in front of me regarding the Miller effect, which I was like, I'm not going to cover. So effectively, whenever we have a feedback capacitor, so like that capacitor C mu, which is bridging the base to the collector, we can split it up into only a capacitor connected between the base and ground and a capacitor connected between the collector and ground. And that treatment is what's called pole splitting. So we'll see that depending on the amount of feedback applied, which gets into feedback amplifiers, another thing that we have yet to talk about, we can push poles one direction or the other in order to make our device stable over a large range of frequencies. So that's how we get around instability problems, because anytime that we have a pole, we have a potential for instability. And if that pole occurs in frequencies we intend to use this guy on, that's a problem.
Yes.
So we use pole splitting to push a pole to very, very low frequencies where it doesn't matter because we're not using it for that, and extraordinarily high frequencies where we wouldn't use it for that, so that we extend the width of our midband fringe. Those are all, that's like, I don't know, a 5-minute encapsulation of what we're going to spend the next 2 months on. So, have no idea. Never taken a controls class in my life. Very probably yes, but I honestly don't know the answer to that question. Seems extraordinarily likely because it's all doing roughly the same thing. Yeah. All right, circling back around to what we're supposed to be talking about today. So, typically speaking, C pi is much larger than C mu, which is larger than CCS. Now, unfortunately, these values are not specified on data sheets or anything like that. So we have to experimentally determine them when we are designing a circuit. All right. I don't know. It is fundamentally very annoying when it's like, you need to know these things to properly design stuff. By the way, we have no. I think one of the biggest reasons is because the values can vary so much from process run to process run. Because if you had, let's say that the ion implantation of your base layer or something like that ran 10 seconds longer in one process than another. That means that the thickness of your base is going to be slightly larger, which is going to change things by a pretty large amount. Like, so I think it's just because so many small, subtle things can cause such a large influence on what those quantities could be, that giving you a value actually wouldn't mean anything because there's no reliability there. Does that make sense? That would be my best guess, is their quantities to where there's not really a statistical average that has any actual use to tell you. So
Give
it's
us a bell curve.
probably should, but they don't. They might give you, they actually very often, they do give you curves and all that kind of stuff, but yeah. So anyway, so C mu and CCS can be experimentally determined. CCS, thank you, Bailey. I forgot a letter there. Experimentally determined by measuring the capacitance seen Hold on, sorry. My notes here are literally missing a conjunction and I'm trying to figure out what it's supposed to be. Because I have written CVU and CCS can be experimentally determined by measuring the capacitance seen base and collector. So I feel like it's between the base and collector. So that's what I'm going to go with. Or collector substrate at the desired reverse bias. Right, so those are literally reverse bias junction capacitors. So if you apply a specific voltage across them that you expect your device to be operating at, you just measure the capacitance using an RLC bridge or something to that effect. Actually, you'd probably hook it up to an oscilloscope, apply a fixed amount of voltage and measure the impedance and then back calculate what the capacitor is based on the frequency that you're looking at. But anyway, this is a relatively simple experimental measurement to carry on. Okay. To determine C pi, we must look at the frequency dependence of beta, or HFE, as it's listed in most data sheets. Okay. So
Is that VFE?
that's H, lowercase HFE. So the frequency dependence of beta is usually literally given on a data sheet, but we are going to kind of look at a frequency dependent model here, okay? So we're looking at this as if we are injecting a base current into the system. So this is our base terminal. This is our emitter terminal. Here's R pi, V pi. Here's C pi. Here's C mu. Here's GM, sorry, VBE, my old notes, my apologies. GM VBE. Here's R naught. Here is CCS. This whole bottom node is ground. And one thing that it is not intuitively obvious that we are going to do, so I'm going to explain that, is we're going to short our collector and emitter terminals. Okay, so let's talk about briefly why that is, and the answer is actually kind of obvious. Beta is the common collector current gain of the system. So we're making the collector the common terminal. This tells us how our device behaves. So we measure the current IC, and the ratio of IC to IB is the common collector current gain, which is literally what beta is. All right, so I'm going to call this node X. What time does this class end? All right, we're going to do MOSFETs Friday then, because we don't have enough time to get through MOSFETs too. Okay, so if we apply KCL at node X, what we are going to have so let's see, the current's flowing in. Sorry, I'm trying to follow my own notes here, so I apologize. We're applying KCL at node X. Okay. All right. Things are making better sense now.
I'm not sure I understand.
Shut up, watch. All right. So currents flowing in is going to be VBE over the impedance of C mu. Okay. So correction should be VBE minus VX. Why am I saying? All right, this is a good stopping point because I can't understand my notes.
Shouldn't your current be like IB, R pi, GM1?
So we have to, the problem here is that we have to take into account the impedances of all of these capacitors and stuff like that. Okay, so I know for sure the current of IC is flowing in because none's going to branch off and flow through this impedance. None's going to branch off and flow through this impedance. So I have IC flowing in. I have GM VBE flowing out. Well, I'm trying to figure out what the current flowing in is. So the potential difference between here and here is obviously just VBE. I'm dumb. X is 0. Okay, we don't have to stop it all now. I figured it out.
Yeah, it is directly attached to ground.
Yeah, all right. Resuming things. Sorry about that. I do understand my notes. Okay, so because node X is ground. All right, there we go. Sorry about that. VBE times S C mu, right? So this is the voltage divided by the impedance of capacitance C mu. So 1 over S C mu. VBE divided by that is just VBE times SCU plus IC is equal to GMVBE. Okay, are we okay with this, Luke?
Yeah.
S is the Laplacian operator S because we're in the frequency domain. Okay,
Shit.
so instead of using J omegas and all that kind of stuff, we're going to simplify by just using S. So anywhere we had a J omega, we're just going to put S because that's less writing.
Yeah.
Really, S is sigma plus J omega because there's a real part to the complex frequency and all that kind of stuff as well, which you guys should all know about at this point. But we're dealing in the Laplace, we're going to be doing a lot of analysis in the Laplace domain. I guess I should have prefaced things by that. So that's how we're going to handle impedances. Laplace domain, where S is our natural frequency in the Laplace domain.
That sounds perfect.
Yeah, let's go with that for now. All right, so the current flowing in, VBE times S C mu plus IC is equal to the current flowing out, GM VBE. And so we can rearrange this and find that our current IC is GM minus SC mu VBE. Using Ohm's law, VBE is simply IB, our base current, times the parallel combination of R pi 1 over S C pi and 1 over S C mu, which looks like IB divided by 1 over R pi plus SC mu, excuse me, SC pi plus S pi plus S. Okay, are we okay to this point? Anything seem bad? We are literally almost done here, okay? Beta is defined as the ratio of IC over IB. So that's GM minus SC mu divided by 1 over R pi plus SC pi plus SC mu, which can be approximated when GM is much greater than SC mu to be GM R pi divided by 1 plus S C pi plus C mu times R pi, or beta naught, so our DC value of beta, divided by 1 plus S C pi plus C mu times R pi. So this tells us how beta depends on frequency. It was our ultimate goal in the first place. Okay, so if we were to plot this, the magnitude of beta measured in decibels would look something like this. So here's beta naught. And then I'm going to define this frequency as omega b. And I'm going to define this frequency as omega t. And so a simple Bode plot of this would look something like this, where this slope is negative 20 decibels per decade. Omega b, our corner frequency here, is just 1 over R pi times C pi plus C mu. And this corresponds to 0 decibels. Omega t, beta naught times omega b is our transconductance GM over C pi plus C mu, which is going to be approximately equal to GM over C pi, and FT is then GM divided by 2 pi C pi plus C mu, or approximately GM over 2 pi C pi. So omega t and F of t really just represent the unity gain bandwidth in radians per seconds or in linear frequency. So effectively, if we know where the gain of our transistor amplifier hits 1, and we know the transconductance we have, we can determine the value of C pi. Andrew?
Just a derivation.
No, nope, not at all. Not even a little bit.